Jupiter's Great Red Spot has always been a swirl of mystery in our solar system. For centuries, recently, researchers have uncovered compelling evidence suggesting that the storm we see today is not the ancient one observed by early astronomers like Giovanni Cassini. Instead, it appears to be a younger, dynamic storm that has undergone significant transformations in size, shape, and intensity. In this video, we will delve into the recent research that challenges our previous understanding of this Jovian feature, explore the historical observations that have tracked its evolution, and discuss the broader implications these findings have for planetary science and our understanding of atmospheric phenomena on other worlds. Recent observations by researchers suggest that the storm we see on Jupiter today, known as the Great Red Spot, might not be the same one that astronomers observed centuries ago. The research, led by Austin Sanchez LGA and his team, has used a combination of historical observations and advanced simulation models to study this mystery. Their findings suggest that the storm we observe today actually formed less than 2 centuries ago, which is quite recent in cosmic terms. This revelation came from analyzing data collected over decades, including those from the Hubble Space Telescope and the Juno spacecraft, which showed that the Great Red Spot has been changing. In simpler terms, it's not only shrinking but also rising and becoming taller as it gets narrower. This is contrary to the storm's historical depiction as a stable and permanent feature of Jupiter. Exploring further into these changes shows that the dynamics of the storm are profoundly complex. Jupiter's atmosphere, predominantly made of hydrogen and helium, creates the perfect environment for sustaining long-lived storms like the Great Red Spot. Yet its persistence and transformations are influenced by factors such as atmospheric pressure, temperature gradients, and jet streams. The research utilized computer simulations to demonstrate how shifts in these atmospheric conditions could lead to significant changes in the storm's structure and behavior, seamlessly connecting past observations with current theories. Additionally, researchers have observed an intensification in the storm's color, turning a deeper shade of red. This alteration could be due to changes in the chemical composition of the clouds or the altitude at which these colors are being observed. At higher altitudes, these chemicals are exposed to more ultraviolet radiation from the sun, possibly affecting their visibility and coloration, providing a bridge to a deeper understanding of atmospheric chemistry on Jupiter. Moreover, the shift in the storm's speed and direction has also intrigued interest. Historically, the Great Red Spot drifted westward across Jupiter's surface at a relatively steady rate. However, recent observations indicate that this drift is accelerating, suggesting that internal dynamics or shifts in global wind patterns might be influencing the storm's movement. This research helps refine models of atmospheric dynamics, offering insights applicable to other planets, including Earth. For instance, by studying how storms on Jupiter evolve and dissipate, scientists can gain clues about the behavior of long-lived terrestrial weather systems such as hurricanes and typhoons. Since the 17th century, the Great Red Spot of Jupiter has captured the interest and imagination of astronomers, beginning with Giovanni Cassini, who first noted it around the mid-1600s. Initially described as a permanent spot, this remarkable feature marked one of the early major discoveries in planetary science following the advent of the telescope. Observations from the 1800s suggested that this storm was large enough to fit 3 Earths side by side. However, as we mentioned, more recent measurements indicate that it has been steadily shrinking and changing shape, and this reduction in size has been documented steadily since the late 19th century. Interestingly, the reasons behind this shrinkage remain a topic of active research and debate among scientists. The continuity of the storm has also been questioned. After the initial observations by Cassini, there was a period where the Great Red Spot seemed to disappear, with no recorded observations from the early 18th century until it was rediscovered in the 1830s. This led some researchers to speculate that the modern Great Red Spot might not be the same feature observed by Cassini, but rather a different storm that formed at the same latitude. The compilation of historical and modern data provides a unique timeline of the storm's evolution, which allows us to trace the morphological changes over time on Jupiter. It turns out that Jupiter's enormous magnetic field plays a pivotal role in Jupiter's storm dynamics, influencing everything from storm longevity to auroral activities. Jupiter's magnetic field, the strongest in our solar system, extends up to 15 million kilometers from the planet, making it the largest magnetosphere around. This colossal magnetic shield traps charged particles, creating intense radiation belts that interact with the atmosphere, potentially affecting weather patterns and storm behaviors like those seen in the Great Red Spot. The interaction between Jupiter's magnetic field and the solar wind leads to spectacular auroras at the planet's poles, much stronger than Earth's. These auroras provide crucial clues about the interactions between the magnetic field and solar storms. Such storms compress Jupiter's magnetosphere and can shift its boundary with the solar wind inward by over 1 million miles, impacting atmospheric dynamics on a global scale. Furthermore, the magnetic field's interaction with solar storms produces significant X-ray emissions, which are most apparent during the intense auroras. These emissions offer insights into the strength and structure of Jupiter's magnetic field and its influence on atmospheric phenomena. For the Great Red Spot, the magnetic field could be a key factor in its dynamics and longevity, as the charged particles within the storm may interact with the magnetic field, altering its stability and lifespan. The insights gained from studying Jupiter's magnetic field and its effects on the atmosphere extend beyond just one planet. They are critical for understanding magnetic environments on other gas giants in our solar system, and can even apply to exoplanets and other star systems. By analyzing how Jupiter's magnetic field interacts with its atmosphere, scientists can better model how exoplanetary atmospheres might behave under similar conditions. We hope you enjoyed the journey through the mysteries of Jupiter's Great Red Spot. Thank you for watching, and don't forget to subscribe to Astrosphere Hub channel for upcoming space videos.